and welcome to the first lecture on computational electromagnetics, which is a review of vector calculus. So, as we will find out in this course, the whole language in which this course is taught or spoken is the language of vector calculus. So, it is important that we become comfortable with some basic ideas that are useful for electromagnetics. Vector calculus is a very vast area. We will cover only those parts which are relevant to electromagnetics. Okay. So, these are the topics that we will cover in this module. We will start with the chain rule of differentiation, introduce the idea of the gradient, move to the three most popular operators that we will find: the gradient, divergence and the curl. There are some very important theorems in vector calculus that we will talk about, and then some of the corollaries which are like the tools and techniques used in this area. Okay. So, starting with the chain rule. So, let us start from the beginning. Alright. So, let us consider a scalar function, okay, a scalar function, and let us say it is of 3 variables. It could be of any number of variables, but we will stick with 3 because we live in a 3-dimensional space, it is easy to visualize. So, something simple could be, for example, here is a charge plus q and I am standing over here, and there is some distance over here, there is a vector r that connects the source to where I am. And this observer here could be recording, let us say, the electrostatic potential. Right. Now, we all know that from high school that potential is simply given by a simple expression minus q by 4 pi epsilon mod r, where mod r is square root of x square plus y square plus z square. Okay. So, now you have this function f over here, which is a function of 3 variables x, y and z. Okay. Now, let us say that this observer wants to change in wants to move in some direction, and this direction could be arbitrary, and I want to know how does the potential change. So, in other words, what is this delta f if there is some arbitrary change in the direction of the observer. Okay. So, in other words, to make it precise, so let us say x changed from x to x plus dx, similarly y will go to y plus dy, and z goes from z to z plus dz. Okay. We want to keep it as general as possible. So, again, this is something that we studied in calculus in high school, the so called chain rule. So, chain rule tells us what is the total change in a function given changes in the composite sort of variables. So, this df will be given by a set of summation of the changes due to a change in x, due to a change in y and a change in z, right. So, this hopefully is familiar to all of you, the chain rule over here. Note that these are partial derivatives, okay, because the function depends on all 3 variables. This only takes the derivative with respect to one of the variables. Now, when I look at this expression, while this is correct, there is a more convenient way of looking at the same thing. So, if I look at this expression over here, I can think of it as the dot product between 2 vectors, right. So, I can say that this is, let us say, the dot product between 2 vectors v dot u, and that, for example, v could be this vector and u could be this vector, right. So, what I have got is this change over here df is the dot product of 2 vectors, and this vector over here is something which appears time and again. So, this is defined as the gradient of f. Okay. So, it is a vector, and so it has 3 components over here, and this is the shorthand notation for it. This over here is the displacement, right. So, this is the observer's displacement. I can as well write this as something like dl. Okay. Usually in this course I will not be putting an arrow on top of the gradient of f, but it is understood that it is a vector. Another thing I want to point out is that this is a shorthand notation. So, I have written it in brackets with 3 components. That means that it is a vector with 3 components. I can as well write it as like this: gradient of f is equal to x hat, y hat and z hat. Okay. You can see that this takes more time to write than this. So, I am going to use this more often than not. It is understood when you see something with in brackets with commas, it is a vector that I am talking about and its components. Okay. So, this was about the chain rule, which gave us a very convenient way to arrive at the idea of a gradient. Okay. So, this is the gradient. Moving on, now let us try to work with this gradient that we have defined. So, from the previous slide we had calculated this total derivative df and wrote it as a dot product between the gradient over here and the displacement vector over here. Okay. Now, once you have written a differential element, as it is called, the next objective would be to find out what is the total change. Let us say when I go from some point a vector to some point over here b vector. Okay. So, for example, I could go like this. So, this is the integral that I want to calculate. So, for example, this df could represent a differential or a small amount of work done, and I want to find out the total work done. So, I have to integrate along the path. Notice that the limits of the integration are simply a and b. The route is not being specified. Okay. So, it is not, this is not the only route possible. I could, for example, have gone like this, okay, or any complicated route, right. I could have gone like this. Does not matter, it is not specified over here. So, what you can see is that when I start integrating this df, right. So, I know that if I just write integral of df from a to b, right, if you did not know anything else, you would simply write this as the value of the function at in this way fb minus fa, right. But now we also have a nice identity for df, which is in terms of the gradient, right. So, this is the relation that we arrive at, okay. And the remarkable thing, of course, is that this expression over here is path independent. It did not matter which path I took, because this is a complete differential over here. The result depends only on the final point and the initial point, okay. So, you can see immediately a very straightforward corollary of this is that if I am going from one point back to the same point, right. So, in other words, the final and the starting points are the same, then this is true, right. The integral over a closed path. So, when I put on the integral sign a loop over here like this, it means that it is an integral over a closed path, starting point, initial point is the same, and this is going to be 0, right. Some of you may have encountered such expressions earlier. So, these kinds of forces, if a force is of the type grad phi, we call this a conservative force, right. So, for example, we know that the electrostatic force is a conservative field. So, it does no work over a closed path. Not all forces are conservative. So, this is a special case. So, we have got some idea of how to work with the gradient now, okay.